This is the first calculus video, and the first thing we're going to do is discuss the concepts required to gain a better understanding of calculus, and then we will be leading on to the actual calculus concepts further on down the line. So first we're going to be talking about something called limits. Limits is a very important concept to understand for understanding calculus as well, as I've said before. So first let me talk about the definition of a limit, and then we'll try and talk about it a bit further. A limit is the value of the function, and remember the function is y, so it's the value of the function, which would be your y number, to which the graph approaches, so as it's going towards it or leaning towards it, as the value of x approaches a certain value from both the left and the right. So I'll read that again, but then I'll try and explain a little better. A limit is the value of a function, which would be a y value, to which the graph approaches, so as it's getting closer to it, as the value of x approaches a certain value itself from both the left and the right. So first of all, it's important to understand that limits are used to help us to examine the behavior of a function around a certain point. And then it also allows us to study a number from further away. In other words, we can study the points around in order to better understand the given value that we want to know more about. The word approach is a key word in understanding limits. We're talking about approaching something. A graph is approaching another value. I think in the beginning, this is a difficult concept to understand, but I'm going to try and show you something now which will explain it in a more visual format rather than listening to words and what it means. So let's consider this function. F of x is equal to x minus 2 multiplied by x plus 1 divided by x minus 2. Now it's probably not a common looking function to you. If we multiplied out the top, it's a quadratic, and at the bottom in the denominator we have a linear function, which may seem unusual, but consider that if we simplified and we said x minus 2 goes into itself once and into itself once, then our new function is a straight line. It's a linear function. So let's draw this function on the board and have a look at it. So if we have the function y equals x plus 1, that means it must have a y-intercept of 1. If we find the x-intercept, we'll find that that is minus 1. Normally, I'll explain shortly why I'm saying and normally. I'd like that to go a little bit further. Just want to move that out the way, apologies. So we said f of x was equal to x plus 1, and we're drawing in our line, and that's what it would look like. However, we need to go back and consider this denominator. Is there a value for x that could make that denominator equal to 0? I hope you agree that if x is equal to 2, we would get 0, and therefore this function would be undefined because we can't divide by 0. So clearly x equaling 2 is a problem for us. And in fact we would say that x cannot equal 2, because if we make x equal to 2, this function would be undefined. So if x cannot equal 2, we need to find where x is 2, and we need to make a hole in the function, because x cannot be that number. So it would look, sorry it's not very straight, but it would look something like that. So that entire function is all normal, like you would draw a straight line, but because of when it was in its original form, if the denominator was equal to 0, that would be a problem. So therefore we have made a hole in the function where that x is not allowed to be. So let's first calculate something to do with that value. What if we made x equal to 2? So in other words, in our function format, if x is 2, then f of x, which is the same as y, would be 3. So in other words, this is the coordinate 2, 3. My spacing is not very good, but just run with me for a second. So now, when I talked earlier, I mentioned to you that we were looking, when we talked about the concept of a limit, that we said that we would look at a value of the function to which the graph approaches as the value of x approaches a certain value. So our certain value that is important to us now is this 2. It's the key part of drawing this function correctly, because we have to figure out that x cannot be 2. So if we look coming in from the left-hand side, and notice we're looking at x numbers, so I'm going to draw it like this coming in from the left-hand side instead of going up the line like that. So as the x number approaches 2, so maybe first it's -1, so that would be this point here, and then I get, as I'm going along this line, I get to where x is 0, and as I keep going along the line, I get to the point where x is 1. And then as I'm approaching it, what y number is being approached at the same time? The y number being approached must be 3. Now let's consider, I'm going to have to remove something here, otherwise it's going to look a little bit too busy. Let's draw a little bit more of the line. Let's consider if we decide to approach from this side. I would first maybe come across where x is 3, and if we go back to here and put 3 in, that means that we're approaching the 4. We're at the 4 at the moment. That would be the point over here where y is 4. And I keep on approaching, and as I get closer to where x is 2, so I'm approaching it, it becomes a limit, because y can never actually equal 3, because 2 is not really part of this function. So that's the whole idea of the limit, and as far as you can possibly go. So we can approach from the right-hand side. We can get closer and closer and closer to 2, and therefore we are getting closer and closer and closer to the 3 as the y coordinate, the y value, but we can't ever reach it because of that hole in the function. So I hope that's given you a better idea at the moment of what a limit is, as opposed to when we were looking at the definition. So a little bit of a review. First, let's think about what is a limit. A limit is our best prediction of a point that we cannot observe. So yes, we can observe the hole here, so this one makes it a bit easier, but essentially you're imagining something that cannot happen. If you remember the original function, we had this, and because we had a variable in the denominator, we knew that there was a problem there. So that's our focus. A limit is our best prediction of a point that we cannot officially observe. And how do we make the prediction? We almost zoom into the neighboring points. We come in from the left, we come in from the right, we're looking at all the points in the neighboring vicinity to try to estimate, in other words. So we're zooming in as close as we can. So we have to imagine that that is a hole, as we've made it actually, and you obviously don't want to fall into it. You're coming closer and closer to have a look around it. And why do we need limits, really? In general, mathematics has things that we could call a black hole scenario, things like dividing by 0, which we were looking at this one, or going to infinity. That seems like a big black hole. So therefore, we have to have this understanding of limits to give us an estimate when we can't compute the result directly. You see, if I put 2 into x's place here and put it into my calculator, I would be told there was an error because I'm trying to divide by 0. So now let's have a look at the kind of questions you can get asked regarding limits. So this is how it would be written and said. We are looking for the limit as x tends to 2, so it's going towards 2, on the function 3x squared. First of all, in this case, I'm sure you can clearly see there's no denominator. We're just looking at 3x squared. So there's nothing that can cause this function to be undefined. So therefore, all we have to do is simply substitute 2. So we'll set it out like this. The limit as x tends to 2 of 3x squared. would be equal to, I am putting 2 into x's place, and you simply do that calculation. So that means the closer you get to 2, whether you're coming from the left through all the negative numbers and 0 and 1, or whether you're coming from the right, 5, 4, 3, and so on, the closer you get to where x is 2, the closer you are going to get to the y value that is 12. So that should be a straightforward one, but also understand what it is you're finding. Let's have a look at the next one. The limit as x tends to negative 3 of the function x squared divided by x minus 2. Now in this case there is a denominator. But if you consider what the limit is that we're looking at, the limit isn't the number that makes this denominator a problem. The value of x that makes this denominator a problem would be 2, because then we'd be dividing by 0, 2 minus 2. So because the value that we're tending towards is not the one that causes the trouble, it's very similar to the previous example. The limit as x tends to negative 3 of the function x squared divided by x minus 2, I simply substitute negative 3 into x's place and do the calculation. So negative 9 over 5. And now let's consider the next one. Now you can see we're going to start getting towards those that cause problems. We're looking for the limit as x tends to negative 5 of x squared minus 25 divided by x plus 5. Notice that there's a variable in the denominator, so that should always ring alarm bells in our head. If we put the number we're interested in finding, the limit, if we substituted that in, you will see that now you will make the denominator 0, and therefore this function, the answer here, will be undefined. So in this case, we have to be a little bit more careful. So at the moment you can almost see it as just a warning sign that there is going, when we substitute, there's going to be an issue. So we're first going to factorize the top, because if I go straight onto the step that I've just gone on to, I'm going to put negative 5 in and I'm going to divide by 0, and therefore I can't find a solution. So instead, sorry, I've left a step out there. Because I'm not busy substituting, and this is important and also for later on when we do other calculus concepts, I need to keep the limit here. In fact, I'm going to write it underneath and I'll rub it out later. Would be better set out like this. So I'm still saying the limit is tending towards negative 5, because at the moment I'm not substituting the negative 5 into x's place yet. I have a difference of 2 squares at the top, so therefore I can factorize. That goes into itself once and into itself once. So my actual function I'm looking at, and I'm still not substituting, I just want to see what the function looks like. And now finally I can substitute, because I can get an answer. I'm not going to get an undefined anymore. I'm going to put negative 5 into x's place, and my answer is negative 10. So notice it's really important that until you actually substitute whatever you're tending towards into the function, you can't leave out what the limit is going to be. That stays in part of your working. So the limit as x tends to negative 5 in that function would be negative 10. Okay, let's look at the last one. I'm just going to write it up here as well. The limit as x tends to 2 of the function 10. So here this may look a little odd to you, because now you're going to wonder, well, where am I going to put the 2, because there isn't an x. But consider what the function 10 looks like. The line y equals 10 is going through where y is 10. That is the line y equals 10. And we are interested in what happens as we approach from the left, getting towards 2, and what happens as we approach from the right. And I think you will see quite clearly that the only value we can possibly be approaching is y equals 10, because that's the only value there is. When I'm approaching to 2, when I get to where x is 0, y is 10. When I get to where x is 1, y is 10. Coming from the right-hand side, when x is 3, y is 10. So the only thing I can possibly be approaching towards as I'm getting closer and closer to the 2 is 10. So the limit of the function 10 when x tends towards 2 is 10. But the next important idea and concept to be able to understand calculus better is average gradient. You found this before when you did functions in grade 11 and possibly even grade 10, where you had 2 points, or sometimes had to calculate it, but you have 2 points on a curved graph, in this case a quadratic, a parabola, and you had to find the average gradient of the curve. The reason it's the average gradient, because if you're looking for the gradient between one point and another point on a curve, you're looking for the gradient of this. But by finding the equation of the straight line that joins those 2 points, you have found the equation of the straight line and not the curve. Hence we call it the average gradient. Because you've got the points, this should be very straightforward. You have 2 points. In other words, we have an x1, y1 and an x2, y2. We use the gradient, change in y over change in x. We substitute the numbers we have. Be careful here because you are subtracting -3, so you're going to get a plus. And if you calculate that, you should get -4. And the line is sloping down, so that should make sense. So we have a gradient of -4. So this line that we found the average gradient of, it was quite close to the curve. If I'd asked you to find the average gradient from here to here, you would probably think, well, that's not really an average gradient of the curve because it's quite far away. My question is, do you think there's an even closer one we can find? You know, maybe we can have a point here and here and find that. So that didn't draw a very straight line, but that would be even closer. That would be even more accurate. I think you can agree. But what I'm more interested in is saying, what if I got closer and closer and closer and closer to one of those points? So instead of just choosing 2 different points, maybe get a point that's closer to the point C and find that. And then maybe even closer and find that. And the closer and closer that we're going to get to point C, sorry, I didn't mean to cross that out, I thought I was erasing. The closer and closer we get to point C, what you'll find is that eventually you'll be right on top of C. I haven't drawn that too well, but I hope you can see that. And what you'll have actually drawn is a tangent. So the closer and closer and closer is quite important because that's where the idea of limits starts coming in. So if you now look at the tangent that we've drawn here at the 1 point, we want to explore that whole idea a little bit further, and that's something that we're going to be dealing again, as I keep saying. We are going to be looking at the actual calculus concepts later, but all of these are going to lead to a better understanding of that. So let's consider this drawing I've got here of a parabola, a quadratic. If we saying that this is any x number, doesn't really matter what it represents. I hope you'll agree that then this coordinate would be x, g of x, because our function is called g of x, so that would be the corresponding y number. So that's a nice general coordinate, so we're not going to talk about specific numbers like we did in the previous slide. Now let's consider this point Q. Now it's also an x number, but we've obviously added some on. So I'm going to call this x plus h. H could represent anything. I've added something on. I've gone further along the x-axis. So my x number at Q is called x plus h. So from a functions point of view, remember when you learned function notation, we asked you maybe g of 2, so you put 2 into x's place and found the answer. And what you'd really found was the coordinate on that function when x is 2, y is 4. What if I asked you to put g of x plus h in there? You would then have to put x plus h into x's place in the function and do that calculation. But at the moment we're just going to call the corresponding y value g of x plus h. So if I wanted to find the average gradient between P and Q, normally we would then say gradient is change in the y numbers divided by change in the x numbers. So now we need to give these x and y coordinates their proper name. So we're going to call this x1, y1, and we're going to call this x2, y2. So the gradient formula is now going to look a little different. It's going to take the y coordinate when we added a bit more on, and we are subtracting the previous y coordinate. And then the difference in the x numbers is the x coordinate when we added something on, subtract the original x coordinate. And as you can see at the bottom, we can simplify that by collecting like terms. X minus x is nothing, so we're dividing by h. So I hope you can see that whether we use this, what might look like a strange looking new formula to you for gradient, I'll be explaining this in more detail in the next video, and we'll be using this idea to explain the next concept and your first major concept in calculus. I hope you can see that whether you use that formula or whether you use this one, you're going to still find the gradient between 2 points. So in the next video, we'll be discussing calculus concept number 1.